Good evening, everyone. I'm re-uploading section 2, 4.2, Defining the Atom. We're still in chapter 4, unit 1, the structure of the atom. So our aim for today is how has the structure of the atom evolved over time? Our key vocabulary terms are atoms, cathode ray, electron, nucleus, proton, and neutron. So after all this, they define the atom as the smallest particle of an element that retains the properties of that element. So keyword to take from it, particle of an element that retains the properties of that element. So it's not the smallest thing that is made of, just the smallest thing that retains a property of an element. So a lot of you had questions like, oh, if no one had ever seen an atom, how do we know it exists? We actually can see an atom. It's this really cool instrument called a scanning tunnel microscope, and it actually allows you to see individual atoms. That's how we know they exist. And so people also ask whether Dalton and Democritus were correct as terms of if are atoms divisible and destructible. They thought they weren't. But we actually know that they are divisible because we know they have subatomic particles, and even those subatomic particles have subatomic particles like quarks, and they are destructible. They just release a lot of energy when they're destroyed, so it's a little dangerous. So the electron. So once proven, they had a few questions like, once proven that the atoms actually exist, there were new questions like, what do atoms look like? What are they composed of? So the first thing that was discovered was the electron. So the thing that helped like clarify that, they knew that there was like atoms that had kind of like an electrical charge to it. So they actually used this cool thing called the cathode ray, and so when electricity is applied to this ray, it creates this like ray of radiation that travels from the cathode to the anode, and I believe the cathode is negative charge and the anode is positive. We'll see that in the next slide to confirm. And the cathode ray, it carries a negative, it was carrying a negative charge, and that negative charge particle is what we now know as an electron. So in the cathode ray, they were seeing the existence, the confirmation of electrons. So let's go. This is our cathode ray. So cathode, it goes negative, positive, that's the power source. So when electricity is applied, it creates a charge down this ray. And they were to calculate that it was a negative charge, and that's why they discovered electron. So J.J. Thomson. He measured, sorry, hold on. Okay. J.J. Thomson, he measured the effects of both the magnitude and electrical field of the cathode ray to actually determine the charge to mass ratio, and then compare it to other values. He actually won a Nobel Peace Prize for identifying the like exact mass of the electron. And again, he proved that Dalton was incorrect. So he found that the electron actually weighed less than a hydrogen atom. And for us, we know this. Like, if this subatomic particle is made up of this bigger particle, of course it would have less mass. But back in the day, they thought atoms were the smallest thing in the world. So it was really shocking to them to know that there was something even smaller. And that's why he won a Nobel Peace Prize. No, sorry, not the Nobel Prize. Peace Prize. He just won the Nobel Prize. So next came this guy, Robert Milken. He's like super famous in the physics world. And most all higher advanced physicists will have done this experiment. He did this really cool experiment called the oil drop experiment. So what he did, he had this little apparatus. He sprayed, what did he do? Let me think. Give me a second. Yeah, so in this apparatus, oil was like sprayed into this thing containing oil is sprayed into a chamber. There's a positive and negative. So you know electrons are negative, so they're going to be traveling down. So he sprayed oil into these parallel chamber thingies, and an X-ray would knock out the electrons from the particle in between the plates, and the electrons would actually get stuck in the oil droplets. And then by varying the intensity of the electrical field, Millikan could control the rate of a droplet fall, and then determine that the magnitude of the charge on each droplet increased in like certain amounts, and determine like the smallest common denominator, which was like 1.6 times 10 to the 29th coulombs, which is just a way to measure charge. And then he was the first one to actually define like the charge of an electron. And then that whole number was equated just to -1, just to make it simple. And then now we know that the mass, and then once he found the charge, he actually found the actual mass. Yeah, the mass of because remember, JJ, he did the mass charge to mass ratio. He didn't actually find the actual mass. So this guy, he found the actual mass of an electron, and it was it's like 1/1840, the mass of a hydrogen atom. So what that means is that the electron is 1,840 times smaller than an electron is 1,840 times smaller than a hydrogen atom. Ooh, numbers. So let's go back to J.J. Thomson. If you guys hear me say J.J. Rutherford, always correct me, say J.J. Thomson. So what we knew is that matter was neutral. We talked about this in class, is that we know matter is neutral because we're not always consistently being electrically shocked by things that we touch. So of course there are exceptions, but the majority of things we're touching aren't giving off like an increase or a decrease of electrons. So that's why we don't feel shock, because it's balanced. So J.J. Thomson, they knew that this that matter had an overall net charge, meaning the positive would balance out the negative. So he created this model of an atom. So it was like this circular cylindrical thing with some random negative charges in it, and everything else was positive. And we just called plum pudding. It's like, it looked like a chocolate chip cookie, but they called that plum pudding. So next we go to Ernest Rutherford. So in 1911, Ernest Rutherford, he studied positive electric charge. And so what he did, he pounded gold into these super thin sheets and shot these positively charged alpha particles at that gold sheet. And gold, Au, is an atom, is like an element that's composed of atoms. So an atom. And so what he thought would happen, because he thought J.J. Rutherford's model was right, he thought that most of the alpha particles would go straight through with like some slight like, alteration in path, because these positive charges would be slightly attracted to these negative charges, and so that's why they wouldn't go completely straight. But what actually happened? So this is just an overview of his experiment. Oopsies. Let me go back. So he concluded that he actually I'm gonna go to the next slide. Okay, here we go. So what actually happened is that when he shot these alpha particles through, most of them deflected. Not most of them. Some of them deflected, and some deflected straight back. And then, but the majority of the alpha particles went through with, some not completely straight through again. So like, he knew that J.J. Rutherford's experiment was partially right, but he's like, what's up with these alpha particles, deflecting straight back? So what he concluded, because only some of them did, that the atom had a positive nucleus. That's the only way, so negative attracts positive, and positive repels positive. So once these positive alpha particles came into contact with this positive nucleus, it tried to stay away as possible. So let's go back to his notes. So he concluded that the atom was mostly empty space because most of the alpha particles went straight through. Okay, and almost all atoms' positive charge and almost all of its mass was in this dense region in the center of an atom called the nucleus, and the electrons were held together by the negative and positive electrostatic forces between the electron and the nucleus. Again, so the positive forces between the positive charge and positive alpha particles called deflection, which we talked about already. And then, so he named those positively charged particles in nucleus protons. So now that we know they're protons, they're electrons, and we know that electrons they basically have no weight, and the protons actually only have one atomic mass unit. We're like, the next question is like, where's the rest of the mass? Like, this only accounts for like about half of that element's or atom's mass. So this guy, James Chadwick, he actually won a Nobel Prize for this. He actually discovered a neutron. That's where all the rest of the mass accounted for. And then it had no charge. So putting it all together, based on what everybody said, so we know that atoms are made of three fundamental subatomic particles: the electrons, the protons, and the neutrons. And the atoms are like spherical in shape, and the atoms mostly travel empty space. They have a positively charged nucleus with electrons negatively charged surrounding it, and the chemical behavior of an element is determined by the atom's electrons. So, like today, scientists have determined that protons and neutrons actually are composed of these subatomic particles called quarks, and there's more research. So we now know that these subatomic particles be divided even smaller, but we don't yet know. We can't yet confirm all the information about quarks. So here's just a little overview. This graph must be in your notes, so you don't have to like put table 4.8, but these are the properties of subatomic particles. This will be on your quiz, and this will be on your test. So this chart, absolutely know everything in this chart except for the actual mass. You do not need to put in the actual mass. So I hope you guys had all had a great weekend, and I will see you on Monday.